Hello, in this episode, we'll go over an example using MNIST Classification. I think this is a good way to start to see how SHAP works because you can visually see how this explanation works. Okay, just quickly, eventually what we'll see here is that the Shapley additive explanation, SHAP, stands on also importance feature weight based on game theory. So if you use a digit 2, so what are those pixels that had positive influence in this prediction and which one had negative influence in this prediction? So you can see which dots are explainable. And this is sort of a way of how SHAP explains its results. Let's go over code that tries to do this. Okay, so first, well, I don't need to install Lime. I just put it here just in case for reference. But what I do need to install is the Shapley value package. So let's unpack this package. All right. So if you have just an Anaconda based offline, then you probably have to install the Shapley value package on your computer first, and then you can import the SHAP package. In Google Colab, you do this just like inline, like here, every time you use it, and then do it. Okay. The next package is another one. The PDP box is a popular one. You can install it, but I'm going to skip it because we're not going to use it. So here are the libraries that we typically use: Panda, NumPy, TensorFlow. And here is something for the plotting the Shapley value pictures. So this one you need to run it. Okay, so next are some standard steps of importing the MNIST data. TensorFlow has a standard library, as we have covered before. So let's just download them in the train test. The X train and Y train are the images and the label, which digit it is, and for the test data and training data. And we rescale it, reshape it to flatten it, the 28 by 28 image data, we flatten it to 784 like a row vector, and rescale the each pixel value so that it ranges between 0 and 1. So by dividing by 255. Okay. So this is just a standard thing we do, all right? And because create a categorical variable, which means that there are 10 digits, 0 to 9, and right now the label is given as a number, isn't it? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Instead of doing that, let's just have 10 variables. Each are 0, 1 indicator variables, which if it's a 2-digit, then the indicator variable for 2 corresponding to it will be 1. The rest of them will be 0 and so forth. It's called one-hot coding. Or categorical variables here. Okay, so this creates 10 variables. Okay, so I guess if you care Y train, we can take a look at it. It's like there are 10 digits for each. So for this one particularly, the answer was, the label was 0. So the first column happens to be 1, the rest of them being 0. Here, the last observation in the training data was a digit 8. So everything is 0 except here, the 9th digit. Okay. All right. So that's one-hot coding. So then the network parameters, the input shape, so it must be 784. We can check that. The neural network input is 784. Okay. All right. Let's define the neural network. Let's just have a simple one, just one input node and then 128 node in the hidden, and then the output will be just 10 activation. It's a softmax activation. Right, so it tries to give a probability of which digit among the 10 indicator variables we created which one is the most probable one. Okay. It assigns the probability for each indicator value. Okay, so let's just declare this network. So just if we call it model and we train it. So here we're training the network. I guess we are not going to train fully, just enough, and then see how it works out. Okay, so let's come back when it's done training. Okay, it's done training for 20 epochs, 76-77% accuracy, not bad. So let's have a prediction in the test data. So we give the image for each observation, the image pixel images, and then predict which label it is. Okay. So now comes the real part, the SHapley value method. So let's select a background. Sometimes when SHapley value has to compute every combination of the input variables, which can be a lot. So sometimes to shorten time, we just pick a background of sample images and use that as the comparison of the marginal contribution of each features. In this case, we have 784 pixels, so that can be quite a lot, isn't it? So the first step in SHAP method is that the SHAP has a kernel explainer. There are several different explainers, but here we have a black box. So we need a general explainer that is not model dependent. So we use a kernel explainer and pass on the model here. We created a model, isn't it? The model, the fitted model. So we pass on that model with a background of these 100 images. So we can make a marginal contribution, calculate them against this. Okay? Still, there are 100. Okay? So it can be a reasonably extensive computation. So let's compute the SHapley values for the test value. So for example, the test image, the second test image, X test data 1. Let me just make sure. X test 1. This is one example image, for example. Right? So it's it looks large, but but it's a value ranging between 0 and 1 because we rescaled each pixel image. So this is how X test data looks like. So we pass that to get the SHapley value being estimated. Even with the server, it does take some time to compute it. Let's come back when it's done computing the SHapley value. Okay, it's done computing. So the SHapley value values here there's 784 pixels, okay, and the largest one here is 0.015. Okay. After all the values, the text data, but the particular one that we are right now looking is this one, the X test of 1, isn't it? That's the one that we want to see. Here, this one. So how is it being presented? The one nice thing is of what we call a force plot. So you call the SHAP INITJS and then the SHAP force. You pass on the explainer, the kernel explainer we computed, E, okay? And the expected value of it, the mean value of it, which is here. And the SHapley value of what you want to find out. And this is like just plotting one dot, okay? How each feature, so there are 784 and many of them are ignored. They are very tiny. So these are the positive forces towards making this predicted value 0.09. And these are the blue ones are the negative forces that pushes towards here, isn't it? And it turns out the largest influence is this negative force of feature 97. turns out to be a larger push. Okay? You can also see this in what we call the same thing in a waterfall plot, ignoring all these tiny ones. The major ones are here. Feature 97 with a very large negative influence. The other features, of course, summed together will be having this much. But you can see that which pixel was kind of very important making the decision. Okay. Can show the image here. That was a number 2 plotting this X test of the second element. It was actually a number 2. The Shapley values of the image is the original image is this. The value that actually were positive are here, okay, and the negative Shapley values that contributed in making the decisions are appearing here. So you can see that which are the positive pixels and influencing negative towards that predicting this digit A. So this is sort of a simple example, and you can visually see how Shapley value method works. Thank you for watching this episode.